what do I call this? Welcome to the senior UA Senior Engineering Poster Competition. Please vote for number one. Vote for number one.
Perfect. Thank you, Nika. So this is the UAA College of Engineering poster competition. Here at the end of the semester, we have capstone posters that kind of go over everyone's projects for the semester. And so here in a little bit, we'll get started and go through each poster in sequence. Thank you. And we have our first poster. So here you go. If you could tell us about your project.
So our project is basically trying to figure out what the best range of hertz for music tempo estimation is using EEG data. This EEG data was originally collected by Dr. Blair Kaneshiro for her Stanford University team. And basically what it is we've got selection of 10 songs here. We had 20 participants each listening to those 10 songs, and they were instructed to kind of tap along with the beat, and the EEG data was recorded while they were listening to these songs and trying to keep along. So what our project here is doing is we took that data, we you wanna
So we took these data and spatially optimized it using this function, which was provided to us. And that basically takes from a total of 125 electrodes that is scanning the brain. And then it's choosing the best one suited for our project. And so here we can see the EEG data. This is participant number 3 out of 20 participants. And then this is every participant's EEG data overlaid. And we can see that here, this yellow participant had quite a huge peak at about 7 hertz. And what our project is basically doing is between the range of 3 to 7, 3 to 8, and 3 to 9 hertz, which range of frequencies would improve the accuracy of estimating the tempo of a song from just the EEG data. And we can see that for participant number 3 in song 5, there's quite a bit of large peaks. So for instance, if we were to limit our range from 3 to 8, we would be able to capture this large peak at about 7.9 or so hertz. But if we were to just limit it to 3.7, this would disappear, and then this would be the largest peak recorded. And that is about 6.1, which is 4 times the tempo of the song. Yeah, 4 times the tempo of the song. And this box plot tells us the accuracy of how many people were able to get close to the frequency of the song. So the frequency of the song right here, 1.52. And then we can see that most of the participants were able to do pretty good. We can see a couple outliers as the range of frequency increases. And these are a couple different results. We can see that originally we have a box plot that shows us the first, second, third quartile. And what that basically tells us is how good of a spread the participants were able to get. And basically, we can see that maybe half of the participants were able to get close to the original tempo of the song. And then a couple other participants were a bit higher in frequency. This is song 2. Song 2 is 1.157 hertz. And yeah, most of the other participants were at 1.5 hertz.
The actual frequency of the song. Now, this right here, song number 5, that's where we got some of the best results. It was a really easy song for the participant to kind of tap along to the beat to. What these outliers mean is it could either be noise, like what we see right here, or it could be that the participant was having trouble kind of going along with the beat of the song. For these songs right here, especially song number 2 here, we see a little bit more of a scatter of the scatter plots here, a little bit larger of a range. But as we go down to the 3.7, we see a lot of these outliers disappearing. So that was probably a noise issue.
And we have a couple different charts that show the other songs. Song number 3 is probably one of the more difficult songs to tap along the beat with. As we can see that most of the participants weren't able to get as close to the original tempo of the song and double the tempo of the song. Most of them were in between those two ranges. And if we look at the mean of the participants, we can see that there was a mean peak at about 2.5 and about 1.25. And if we look at song number 3, 1.23, and that makes sense since most of the participants were at 1.5.
Let me ask you one question. Did any of these results surprise either of you?
Yes, so for song number 9, there was a strange result where most of the songs or the participants in tempo range of 3 to 7 and 3 to 8 were in single time. But for some reason, when we plotted the chart results for 3 to 9 hertz, pretty much every participant was recorded as being able to tap along to double the tempo of the beat. So it was strange because 3 to 7, 3 to 8, everyone was in like the first 2.1-ish range. And then when we go to 3 to 9, they were in like the 4.2 range, which was kind of surprising and strange. So I think
that's about it.
All right, thank you very much. Really appreciate it. Thank you for your project.
Thank you.
All of the train is actually distorted from the surface. All right, now I'm gonna get out of the way.
So we have our next poster here. Here you go.
So my game is called Abound. I worked on it with one other person, but unfortunately today they are sick. And the main thing about this is that we implemented this entirely from scratch. So all the rendering, all the world generation, we all had to go and program that in ourselves. as opposed to using a library to go and just draw an image to a screen. And so one of the most visually distinctive features of this is that the world generation, which happens in 5 different phases. The first phase generates the surface. The second phase generates the caves. Phases 3 and 4 smooth the caves. And phase 5 generates the layer of dirt that can be seen here. The world consists of a background layer and a foreground layer. So you can go and walk around, build, and place and destroy blocks. And yeah, that's it.
What was the hardest part of creating the game, or a part that surprised you in about the process?
The hardest part about making the game, I would say, is the rendering. Initially, for other libraries I've used in the past, drawing an image is as simple as saying, draw this image onto the screen at X and Y position. However, for us, we had to go deeper into that because drawing an image onto the screen, despite how easy other programs make it look, it's not actually that simple. You have to go pass in the texture, pass in the location of which you want to sample the texture from, and then pass in where you want to draw the texture at. And then you can go and apply shaders, so you can go and do other things to the texture, like change the colors. And it just gets a whole lot more complicated, because there's also other things like, do you want to draw one image at a time, or do you want to draw 1,000 images at a time? And unfortunately, we didn't have the time to implement the drawing 1,000 images at a time. So our frame rate is not the best, unfortunately. So every single tile is drawn one at a time, which is very slow.
Thank you so much for your project. It looks really cool. All right, so we have the next poster up, and here you go.
All right, so my name is Gus Schumacher. I work together with Danny Melgar, Nika Makareg, and Colby Fletcher, as well as Brian O'Dowd, Tony Hafner, and Dr. Scott Hamill, to develop an alternative for the raising of this bridge. So this is a railroad bridge near Seward, Alaska. It goes over the Snow River, which is a glacially fed river, and as you can see in this picture, experiences flooding events from time to time. This is because of the glacial lake that sits beneath the toe of the snow glacier, which fills up with water and every once in a while releases a massive amount of water into the glacial floodplain, and this bridge sits below it. So there's a risk for overtopping and catastrophic damage of the bridge, so we need to raise it. And so what we thought about doing is keeping the piers and the bridge structure and raising it incrementally. So we use jacks on the existing pier, lift the bridge up 4 to 6 inches, slide this W steel shim in, W section, set the bridge down, raise the tracks and ballast along either side using a railroad utility vehicle that can do that, and then run trains again. So this way we can keep the track open and running freight while completing this construction, raising, like closing the tracks, raising, opening the tracks, doing that incrementally until we get to the top, and then encasing all of that in a concrete pier until we get to our 4-foot raise.
So I've got a quick question for you. So what part of the project did you find the most surprising?
I'd say that, like, considering like all of the other alternatives was maybe the most surprising. We were thinking of some different things to do, and the ideas that are out there for addressing this problem are much broader than we were expecting. This solution seems very simple and mundane, but there are some big ideas out there to solve it.
Thank you very much. Awesome project.
Thank you.
Our next poster up, Rabbit Valley Trailhead Improvements, and here you go.
All right. Thanks, everyone, for coming in, checking out our poster. So my name's Jillian Holland.
My name's Bailey.
I'm Warren.
My name is Charlene.
And our project was the Rabbit Valley Trailhead Improvements. So for our project, our scope was to take the existing Rabbit Valley Trailhead, which is about 24 feet wide, and install a parking lot because it's currently lacking parking facilities as well as pedestrian amenities. So here is our site design that we have proposed. It includes 100 parking stalls. It has a vaulted toilet and orientation kiosk to address sanitation needs, as well as have maps so that people visiting the site have a clear idea of where they're going. Not only does this trailhead access the Rabbit Lake Trail, but also over here, it's the access point to the Flat Top Sunnyside Trail. We have drainage calculations that we have, and we have a 36-inch deep V-bottom ditch that runs here to the north side of the road and ultimately drains through this 24-inch culvert to go off-site. Our typical section over here, you can see with that dashed line is the existing roadway. So essentially what we've done is we've cut into the mountain where it was 24 feet wide. It is now about 76 feet in width. And so we've cut into it and we've flopped that over onto the downhill side, put in a retaining wall, and that right there is how we came up with our roadway. And so we did evaluate a few different retaining wall design alternatives. This includes both the sheet pile retaining wall, the cast in place wall, and the modular block wall. After performing calculations with regards to factors of safety, we were able to come to our decision that the modular block retaining wall is our recommended alternative. So that will be installed here and will be about 700 feet in length, carrying along that entire parking lot through that 40-foot radius turnaround at the end. The project is anticipated to cost about $1.8 million, and that is includes our modular block retaining wall preferred alternative in there. So that modular block retaining wall does take up a fair portion of that estimate. In addition to that, the aggregate required for that structural fill and top course for the roadway is another main consideration. We do, I don't know if you can pan down, have some models here that show both our existing ground and then our proposed surface. So you can see kind of what that parking lot would look like once it was installed. All right.
Awesome.
Any questions?
What was the most surprising thing that you found during the course of your project?
Can I answer that? I think the most surprising thing was definitely all the work that goes into an alternative analysis. My goodness, there was a lot. It was a great process. Definitely lots of help from our mentors. And reading lots of text to figure out how to do that the best way.
Awesome. Well, thank you so much. Awesome project. So we are on our next poster here and for the project, and here you go.
Hello, we're Denali Consulting. I'm Daniel Tedrick, and this is Eric Jenkins, and we work together on the Urban Forest Park vision and pedestrian access corridors. The purpose of this was to take this parcel of land, which is dubbed the Urban Forest Park, and try to rehabilitate it and turn it into something that is accessible and conductive for connectivity throughout the area. So we were providing a menu of options to our client, which was the University of Alaska Anchorage facilities and campus services, various options for enhancing that, providing an alternative analysis and 10% design of the alternatives that we developed. And so we just worked on what we needed to do to meet Municipality of Anchorage and DOT guidelines and make sure that we were compliant with ADA in developing our alternatives. Handing it over to you for the alternatives and for the typical sections.
Yeah, hi. So our alternatives included a lot of different elements. We had everything from a large pedestrian overpass bridge to small bridges crossing Chester Creek, as well as a roundabout, crosswalks, and other safety features. Our alternatives really can be mixed and matched into any combination that is seen fit. And we use a decision matrix to really weigh our alternatives. We have options for both a boardwalk or a developed trail, and then also multiple options for sidewalk improvements as well. One of the biggest issues we had in the area was relocation of some utilities and then also wetland impact. We want to be environmentally conscious with this project and also impact the wetland as minimally as possible throughout the course of construction. So we're good on time there. Awesome.
Ask a quick question here. So I wanted to know if you were surprised by anything that you ran across during the course of your research.
Yeah, so the client had certain visions about what was going on here and what the urban forest park should look like when it was done, and we discovered that those things pretty much cut across the wetland here. On this parcel, it's 20 acres total, 11 of which is type A wetland, which is a valuable wetland that serves more than one purpose, and cutting through that would be a huge cost, as well as taking the time for the credits, and would negatively impact the wetland, which is something that we want to avoid because wetland is valuable and conserving it is important for being environmentally conscious.
Awesome. Well, thank you so much for your project. This is awesome. All right, we have our next poster up, and here you go.
So our project was basically revamping the maintenance practices of the Alaska Sea Life Center. Basically what they've been doing is reactive maintenance, which basically means that they wait until something's broken to fix it. Unfortunately, that leads to a lot of risk due to failure because a lot of this equipment actually supports the lives of the sea animals that are there. And so what we're kind of trying to do is make a bridge between what they're doing right now and a more proactive or preventive maintenance that requires regular inspections, regular component replacements, all to reduce downtime and to basically reduce the risk of failure. And so how we did that was we actually had to go down to Seward a couple times to log the equipment. So we had to take pictures of data tags and then compile them into this equipment list. And so we kind of have them sorted by type, and we made sure to log their manufacturer and their model number especially so that we could look up their installation, operation, and maintenance manuals. Those IOM manuals are actually kind of the most important component of preventive maintenance because they give the manufacturer's guidelines for servicing the equipment so that it can last as long as it says it will. And so using the IOMs that we could find, as well as ASHRAE standards if we couldn't find the IOMs, which was kind of likely because a lot of this equipment was very old. Pretty much as old as the building itself, which is over 25 years old. And so using what we could, we kind of made a tentative maintenance schedule with a time period, the type of equipment, and then each step. And so along with that, we also did a cost analysis where it was kind of like our justification for moving to preventive maintenance, because although preventive maintenance leads to longer machine life, it also has a larger overhead because you have to do more frequent inspections, and sometimes you have to contract out that maintenance, and sometimes you have to replace components, which will also cost money. And so it's kind of like this balance. And so we were trying to make sense of that balance, especially as trying to make it as relevant to the Seward Sea Life Center as we could. And so the result of that, you can kind of see it's kind of different for each type of equipment, and so we're kind of leaving it to them to determine how exactly they want to implement what we're giving them. especially if they can't do all of it because their funding has always kind of been limited and their staff is very, very limited. And so we're trying to make it as open-ended as possible so that they know and they determine what is best for them. Yeah.
Yeah, and the other part that we tried to do with, especially the inspection portion, is when we went down, we realized that a chunk of their maintenance is done by other departments that are deputized into doing maintenance on their specific areas. So trying to make it so that they can, in some ways, if they have to, continue that program with like, hey, here's exactly what we want you to do in this way. So, yeah.
What would you say is the most surprising thing that you found in your analysis?
I'd say like the breadth of equipment that needs work done on it, essentially, like I'd say like the magnitude of what we're trying to do and what the implications could be, because we weren't really sure like how important this was to them until we came and they kind of told us like we're having a lot of issues without a move to make this maintenance more preventive, like we could shut down. And so like we were really aware of like the magnitude of like what was happening until we dived into it.
Well, thank you so much. No, this is great, and I am a big fan of the Alaska Sea Life Center, so I'm really happy that you're helping them out. Thank you so much.
Thank you.
Our next poster up, and here you go.
Hello, everybody. So our client was the Joint Base Elmendorf-Richardson Professional Military Education Center. Essentially, they needed help automating getting students checked in whenever they first show up on their first day of training. So whenever a airman needs to go to the next phase of their development to become a supervisor, they need to come through the education center. And the way that they were checking in students previously was they were just manually inputting their information into Excel spreadsheets. And so they wanted to find a way that was more automated and a lot quicker, more streamlined. And so in order to do that, they purchased one of these little kiosk computers and tasked us with programming it to be able to automatically check in students. So we created a website where students can enter in all their information that they need. Then they generate a QR code, and on check-in day, they come in and they scan the QR code here at the kiosk, and it'll get them all checked in into spreadsheets as specified by the instructors, and make sure everybody's accounted for and get all the required information recorded. So yeah.
All right. So was there a particular challenge that you ran across in your project, or anything that seemed surprising to you?
Yeah. So there was a few issues early on regarding just working with our client in general. Not to say that they were difficult, but there was miscommunications, especially around security aspects of this, because we're handling some sensitive information, right? A lot of there's 300 to 400 students that could be checking in, and we want to make sure that you handle their information in a safe manner, so that way there's no information leaks. So that was a bit of a hurdle, just getting around that and making sure that what we were doing was secure and as helpful as it needed to be.
Awesome. Well, thank you so much. And it's so great that you helped them out.
Yeah.
All right. Poster up, and here you go.
All right. Good afternoon. My name is Paxton Crum, and with me today is Titus Kangogo. Our project here today is a chocolate wrapper for a local candy company, Bird Wings of Alaska. They are a small business founded by a brother and sister duo in 2012. Today they've grown to the point of mass producing large quantities of chocolate, upwards of 800 bars a week in their peak season. Currently, they wrap everything by hand. Sometimes they get help from kids from East High. So we're looking. The point of this project was to help them increase their efficiency in their wrapping process. It was a project. It was a project and a half. The concept is relatively simple, but when we got down into it, there were a lot of problems. There were a lot of design considerations. So we have came up with this final design. It incorporates 3 stepper motors similar to a typical 3D printer to allow movement in all 3 axes because the chocolate requires folding in all 3 axes. So just real quick, how this works is you would place the wrapper on these parts right here, and then you would place the chocolate inside the channel. The motor, you would then press a button where the motors would then take over and perform all the wrapping operations. It is a 7-step wrapping process. So there was a fair bit of time and effort that would need to be put into motor synchronization. Currently, the motors are powered via a Arduino and CNC shield to drive the motors. Our prototype we came up with is largely 3D printed. Some parts are laser cut from wood, and some parts were just picked up at Home Depot. The prototype was a good proof of concept, but ultimately does not meet the standards that we are looking for wrapping the chocolate. However, we believe a properly produced machine following this design would complete the task.
Cool. And so my question is, what was the most interesting thing that you learned throughout the process of this project?
Most interesting? That's a good question. It's a really good question.
It's a little complicated the way a person can really think. So we just had to do a lot of iterations to see how it can be folded. Yeah.
Yeah, like Titus said, we spent a lot of time on the whiteboard going through various iterations. You think one thing might work, but other, oh wait, we have to consider this. So we definitely learned a lot about the wrapping process and definitely how incredible those huge factory machines are in their sophistication to mass produce it.
Well, thank you so much. This is really interesting. I appreciate your project. We have our next project up. It is the Coffee Bot, and here we have someone to speak about it.
Hi, we are UAA Iceberg Robotics. Currently, this is a 2-year project, and we're currently in our first phase. Coffee Bot is intended to be a robot arm inside the coffee shop here in the EIB building, and in our first year, we intended to have at least a robot arm that we can manually control with. So we have a controller here to simulate what it would be like to have the robot arm move. We have currently 6 degrees of freedom, and we have several NEMA stepper motors controlling the degrees of freedom. And Dawson, do you want to talk about the programming real quick?
My name is Dawson Packer. I've been part of the development process this semester for this coffee bot. We decided to 3D print, did you already mention all the parts to help with the development process, since once we were waiting for shipping times, it made it faster to get moving. So starting on the programming, our plan is to have the entire thing, of course, automated by a Raspberry Pi running a Python program that'll interface with all the components. Right now we have a laptop that's doing the same function. We have a Python simulation that is running so that we could have tested all the automation components while the ARM was still being built. Right now they are running in unison, although the lack of limit switches in our robot means they're getting out of sync right now. Anyway, we have about six NEMA stepper motors connected all with their own motor driver, which are managed by the Arduino, hooked up to our controller. Like Jet said, we're hoping to get this thing off the ground next year. Right now we're focusing on a manually controlled ARM that has inverse kinematics implemented in the simulation. We're still working on getting that to the ARM due to many difficulties with balancing torque and speed by our motors. Yeah.
All right. And so I guess my question is going to be, what part of this that you've gotten done so far was the most interesting or the most challenging part?
Yeah, I think that the most challenging part has been balancing that speed and torque. We've been messing with a lot of settings and mechanical configurations to try to get it moving as quickly as possible and as efficiently and safe as possible. And we've been having trouble with our current motor configuration. But that's what I look forward to solving in the future.
And one thing, Dawson, I'm not sure if you already mentioned this, is the issue with the stepper motor and the claw. There is a little bit of a due to the time difference and like delay of the shipment. We ordered this 3 months ago or something like that, and then we got it 2 weeks ago. So we were realizing, the claw and the stepper motor we have aren't exactly how we'd like it to be, but so that one will be currently in revision. But right now we have a prototype to work with. And that was one of the probably difficult parts. I guess the most difficult part, from my opinion, is the shipping. But yeah.
Awesome. Well, thank you so much. This is really cool. I'm always a big fan of robotics in general, so I really appreciate what you're trying to do here. Thank you so much. All right, so we have our next poster up, and we'll just get going. Here you go.
Thank you. So our project was music tempo estimation from EEG data. So basically what that means is we have a bunch of data that was collected using this electrode headset, and it measures the kind of voltage across the brain as a person is listening to a song of music. And what we get is this very noisy EEG data that you can see right here. In our project, our question was, using machine learning, can we, from this data where you can't actually see the beat of the music, can we actually predict what beat this song of this music has? And so we used a couple different machine learning techniques. We used the classification approach and we used the regression approach. And we found out that we were actually able to predict the tempo of the song to a certain degree. It's not perfect, but at one point my model got an accuracy of 85% accurate, so that's pretty good. And yeah, do you want to talk about your...
Yeah, so when we were actually performing any sort of machine learning on these models, we were able to find that there's like regions where this model is able to predict very accurately. So when we're looking at our poster, we can actually see that if we were looking at this, the higher the bar, the more error there is. So within this region, we have the lowest amount of error. So there's a lot of interesting things we can gather from this, such as a major problem in any sort of music tempo estimation, and this includes with just songs themselves, is something called octave error, where we see in our highest frequency, we're getting the most amount of error. And octave error is when something is either half or some sort of multiple of your current beats. So what that basically means is that 75 beats, this is 150 beats per minute, 75 beats per minute is just as accurate as 150 beats per minute. And based on how you interpret that, it could have been, this song could have been interpreted as 75 beats per minute. And what we've seen is that's actually the case, and this provides this data over here with a much larger error, but it also provides us with wrong predictions that this thing is trying to do when it's seeing an 150 beat per minute song, but this data set is actually more in line with what this should be predicting down here. So we need to come up with ways to account for the octave error that we're seeing in these higher ranges, and that would help our data not be so skewed towards this range, where everything over here is also helping contribute to this. And for our conclusions and what we want to try to do in the future is we're thinking about applying multiple different, instead of just using the time domain, we would like to bring in the frequency domain and apply a sort of fusion model approach to our data set. And we were thinking also, while octave error is still a research topic in and of itself that hasn't fully been solved. We need to come up with some sort of approach that makes it so our models see that 75 beats per minute on a certain wave is just as accurate as 150 beats per minute.
Cool. And so I guess my question for you would be, what part of your research did you find the most surprising?
Well, for me, it's actually that with how noisy our data can actually is how we're actually able to decode that there is some sort of correlation between how we perceive music and what the actual music is. And actually, one of the craziest thing that I found in our research is that when you think of a song, your brain actually also your brain will spike at the same beat that song actually was. So that was another crazy thing that I found during this. And that there are certain ranges of music that are more likely to be active when you're listening to music. It was insane to me to find out how complex the brain is and how we actually are able to encode music in such a way that's standard across all of us, so that we can now sort of predict tempos. And
I would say basically the same thing. It was interesting to see that we were getting predictions in a certain range more often, but actually that makes sense when you think about it, because that's where the median of our data set was. That's where most of our data was. So it makes sense that is where we were getting the best predictions, which you can see here and you can see over there as well. Yeah.
I'd say something similar. I think the idea of the octave error was pretty surprising. I just like that concept where you interpret it as like pretty much exactly half the beat or double the beat. I think that's pretty cool to me.
Awesome. Well, thank you so much for your project. It is kind of mind blowing that you're able to detect those things. So thank you so much. next poster up, and which one of you wants to begin?
All right, so we are doing the front suspension as our senior design project. And we had an older design from 2019, but since then there's been a number of rule changes. One of the big ones was the four-wheel drive system that we had to implement. So that changed all of the geometries, and we'd redesigned that. There's a collegiate competition that the Society of Automotive Engineers puts on, and it's an international event, and colleges design and fabricate their vehicles and go compete. And this is the initial process to do that. Our goal was to design front suspension, and one of the big parameters we were thinking about was bump steer, which is how much the tire rotates over a bump, and that'll cause the steering wheel to jerk out of the driver's hands, and that's something we really wanted to minimize. We were able to succeed in going under 2.3 degrees, which we're really pumped about. We did that by making a 2D projection sketch of our suspension members, and kind of with that we figured out a lot of our geometries, and we're able to model it in SolidWorks, which is pictured here. We also had to redesign the knuckle to accommodate that drive axle going through there. And then with all that together, we assembled it and did a finite element analysis in a motion study with a displacement over time function that we implemented from MATLAB. And then initially our stresses were pretty high, so we redesigned a couple of things, beefed the lower A-arm, and then reran the whole thing. Our stresses look good. We have healthy factors of safety. And then with that and our materials that we came up with to meet those stress designs, we came up with a material list and what materials we already have, and then what we need to purchase, because when we go to competition, this is going to be needed as a part of the business presentation there.
All right. And anything to add?
No, he just about covered it. We'd like to thank Dr. Oleg for being our senior advisor. He was paramount in our success. Corbin Rowe, our machinist, did a great job working with us to figure out what allowable tolerances we could use. Matthew Cullen, he was super helpful in getting our FEA motion study put together. And Dr. Pang for being our senior design project faculty professor. Yeah, that's all I got to say.
Awesome. Okay, so I guess my question for you would be, what part of this did you kind of find the most interesting or the most surprising as you were going through, you're trying to fine-tune all of it?
I don't know, probably the FEA. So originally we wanted to do a static study. That's what we were taught in our ME classes. However, with how complex the geometry is and how many mates are involved, we realized that a dynamic study would actually be more representative. And in doing so, we weren't able to mesh at nearly as finely, but at least our model was actually representative of the actual forces that would be applied during competition. But that was a big hiccup. It took us a lot longer than we expected, but ultimately returned results that were allowable and led to success in our senior project.
Awesome. Well, thank you so much. Yeah, no, it's really, really cool. Appreciate it. Maybe my tape is failing. Hold on. All right, so sorry, let's just get started again.
Okay. Do you have to do your intro thing again?
No, you can go ahead.
All right, so our project was the HoloLens 2 guided tour experience. We wanted UAA to have a way to allow new students or faculty members or people just interested in the campus to explore, engage, and educate themselves about our campus. You can do this using the HoloLens 2 AR device. It is a headset that allows you to explore a mixed reality environment where you have holograms, pictures, videos, text, or games even to at each node and point of interest. The reason we created this program was to give prospective students and faculty members a way to explore the campus and have a good time doing it, as well as to promote the AdCell Lab, which is very underutilized in the Rasmussen Hall. It has technology like the HoloLens, as well as AR and AI, and chess for robotic arm chess. So any technology really is in that lab is just underutilized. Ray will talk about the more technical aspects of our project.
Thank you.
All right, I'm Rain. So for the more technical side, we want to actually give it forward to the school and allow future generations of students or faculty to be able to develop further, or at least even just plug and play with what already exists. And so, for example, just twice already today, we had to quickly change the tour on
hold
the
on.
fly.
I think you might have hit the button there. Nope, it's not you. Here, allow me. I'm going to try something here because we seem to keep losing it. Okay.
All right, so I'm Rain. I'm going to focus on the more technical side here. So the other part of the project was also to lay the groundwork for future students, faculty, people to take over this project going forward and be able to extend it as they are able to, and to be able to dynamically change the guided tours on the fly. So for example, we had to just twice alone too, all the posters around, we had to change the posters up or the waypoints up and change the tour to accommodate that. And so it actually is a testament to how dynamic we've laid the groundwork, that at a moment's notice, the points of interest around the map, as well as what they hold, it can be changed. And so that will also allow the venue to dictate what is on the walls, for example, or in the area to be interacted with. Again, it could go from prospective students, it could be seminars as supplementary material. And it just adds another dimension to the surroundings, like to make it more engaging, dynamic atmosphere.
So I guess on that technical level, my question is going to be, what did you find the most challenging or the most surprising that you ran across?
All right, so a lot of learning occurred here. So a lot of database querying, a lot of using the cloud. And so in order to accommodate local anchors that are persistent through space, so we could place them around the university and the HoloLens could identify what locations are being used, it was a combination of incorporating spatial anchors, which take environmental data in, linking that to something in the program to say, this is that type of point of interest. I want to display this interactivity and this visualization. As also be able to leave breadcrumbs around or pathfinding. So it's basically just incorporating the cloud, environmental abstract data with something that's actually physical interactable through the holograms.
Thank you so much. It's really interesting. I appreciate your project. Thank you. Here we go with the next poster, Epidemic Diseases in Alaska and Native History Web Map.
Hi, I'm Robert Hollywood, and that's Mary Collender. And as stated, we made a web map of epidemic diseases in Alaska Native history. Our sponsor was Dr. Maria Williams, who's actually the program chair for Alaska Native Studies here at UAA. And she came up with this timeline of events as part of her own research. Wanted a way to share it online. So we made this map with a combination of Leaflet, which is an open source JavaScript library for doing your classic click and drag, zoom in and out, mark points online map, and OpenTopo Map, which is the actual map map layer you see here. We chose a topographic map over a traditional like street view kind of map because we felt that features like rivers and mountains and just all those things were more relevant to the historical information than something like a road map. It is not in a fully complete state as of yet. We were given a data set of about like 160 events, and each one requires like a fair bit of work to translate into a format that the map can hold. But we do plan on continuing work on this over the summer to fill out the data set and add a few features that we feel we still want to add. We do have a live demonstration set up right here, and we also, that QR code will bring you to the live site, which anyone can access.
So maybe I have more than one question. So my first question is going to be, what was your source for the topographic map, and is that something that's dynamic at all?
The source is OpenTopoMap, which is again an open source tile map is the formal term for the type of map that you would render in your click and drag map. It is, as far as I know, it is like dynamically updated in the sense that like it is. I think it's actually a collaborative project where anyone can go in and add data to it. But it's not something that we would manually edit. But it is something that is kept updated and works at different scales and all that.
And then question two is, what did you find to be the most useful or the most surprising part of what you've done so far with your project?
Yeah, so what we actually found out from this data, which is really interesting, is you can actually see the spread of these diseases in the time frame that they took to get from one side of Alaska to another. So some of the more serious ones, you can see they'll start in the bottom of Alaska. In over a year, they've already made it to the very top of Alaska. So this was something kind of outside the project, after like the technical details of the project, that was really cool to actually see, because I think this is something that's very overlooked in history. But yeah.
Awesome. Well, thank you so much. Yeah, I think that this is a wonderful tool, and I really appreciate it. All right, so we have our next poster up, and I'm going to hand it off to you.
Thank you very much. So we've created a project management tool. The problem is that project management is very difficult. You get a great idea, you start work on a very ambitious project, but eventually you get lost in a sea of tasks and subtasks that you need to keep track of. Our solution is Quayside.app. It's an automatic project manager. You describe your project to Quayside. Quayside breaks your project down into tasks and deliverables. And Quayside tells you what you need to do and what you need to do next.
So once you land on our page, you can log in with either Google or GitHub. You can then create a project by providing a title and description of your project. Quayside will then input this into a predefined prompt that will be sent to ChatGPT that will be tasked with generating tasks that could be done to complete this project. Once Quayside gets that back, it will generate in this nice, neatly formatted graph. You can then sort these tasks by completion status into different Kanban boards, and you can then drag and drop these tasks into different Kanban boards to automatically update it with the database.
So after you've viewed your task in a Kanban and graph format, you can edit your tasks using our edit modal, and you can also edit and share your project with other Quayside users that have logged into our system. This is what we've done this semester. These are our features we've implemented, but we have plans for more features in the future. For example, we want automatic task time estimation.
And we want to integrate with Google and GitHub so that you can track your tasks on those platforms. And finally, we want to have text and email notifications so we can keep you on track to your critical path. And if you want to try it out, it is live right now. Go to quasi.app, or if you're here in person, you can try out our demo.
Awesome. Thank you very much. So I'm going to ask, what was the most challenging part of developing this application?
I think one of the most challenging parts of this was the fact we use Django, and Django really loves to work with SQL databases, but since we were using a MongoDB database, which is a non-relational database, there was a lot of features that we kind of missed out on Django and we had to do ourselves. So things like authentication and authorization, we got to learn a lot about doing all of those things. And I thought it was a fun learning experience, but anything else you guys want to mention?
So yeah, like Maya said, because Django doesn't really work well with non-relational databases, we lose out a lot of the functionality that Django kind of has built in, such as authentication. So that made OAuth and authenticating the user with Google and GitHub kind of difficult. We had to do it all ourselves, but like Maya said, that's a good learning experience. So it's really fun learning how to do that kind of authentication stuff myself.
All right. Thank you very much. I really appreciate your project. And how many users do you have so far?
That is a good question. I don't think we've counted how many users are currently logged in or using it. Currently in its testing phase, we can have at most 100 users, so less than that.
Sounds good. Thank you so much. Really appreciate it. So here we have our last poster, and to present, we have your name, please.
Hi, I'm William Cashmore, and these are my teammates, Garrett, Jacob, Max, and Aaron. We are the double disc anemometer crew. UAA is fortunate enough to be doing solid particle erosion research funded by NASA. That's happening right here in this building on the 4th floor. I'm the undergraduate research assistant on that project, and we had a significant problem to solve. We budgeted. Let me rephrase. In the solid particle erosion research, we are firing lunar simulant particles at a 3D printed sample. These particles and the characteristics of these particles must be defined to a high degree of accuracy. To measure the velocities these particles are traveling at using high-speed cameras and the technology associated with that, it would cost $15,000 to do so. This crew embarked on developing a physical instrument to solve this issue at a fraction of that cost. This is the double disc anemometer. As you see here, this is our nozzle post. We attach our simulant particle nozzle here towards our discs. Our fixed base router spins the shaft between 10,000 to 25,000 RPM. Occasionally, a slot lines up with the particle flow, allowing a package of pressurized air and particles to travel in between our recording disc and our slotted disc. The angle difference between the slot and the impact zone of these particles can then directly correlate to the particle velocity. We see a normal distribution of particle scarring on our recording disk. I hope that this can be seen here. The results of this anemometer, we saw precise and predictable results. As we increased this distance between our slotted disk and our recording disk, we saw a downtrend as expected in our plot here. Our uncertainty was conservatively calculated and was on the order of plus or minus 5 meters per second. We landed well within the range of expected and plausible particle speeds, and it's unbelievably satisfying to see it all come together and work as expected. This crew put in a lot of hard hours and a lot of time into this, and we've fallen in love with it, so it's great to see it come together. So, thank you.
All right, so I guess my question is for everyone here, and we'll maybe just pass the mic around. What was the part of the project that you might have found the most interesting or the most challenging?
Thank you. I found that once you wrap your head around the theory, it seems like you're into it, you understand what's happening. And then when we started implementing it, the rabbit hole just kept getting deeper. So we got to explore really interesting practices that we've learned about. A lot of fluid dynamics, a lot of thermal properties controlling the failure. We've got shaft design, we have bending moments, and it's just an engineering problem to solve. And that was really satisfying to work through with this crew.
Yeah, so I think definitely one of the biggest challenges was just honestly getting started. A lot of times when you're given an open-ended question, it's really hard to find somewhere to start. A lot of times in your academic career, you're given a question with all the information you needed but one, and you solve for that information you don't need. Well, here we had an end goal and nothing in between. And so putting our heads together and coming up with a solid design and going through those steps was challenging, but a lot of fun, and I think we came up with a really solid device. So,
yeah, I think kind of piggybacking a little bit off of what Will said, I think just the jump from modeling and theoretical to how it actually performed was probably one of the biggest hurdles of this entire project in its entirety, and not just the actual operation of the instrument, but the fabrication and machining of every single piece and how that was going to play out. Things that we may have envisioned and wanted, but then we came to machine and just weren't practical or weren't possible. And then an operation of the actual double disc anemometer, expecting it to behave one way and then figuring out it behaves in a completely opposite way to what we're even expecting. And so I think just that knowledge gap between the theoretical and what actually happens was probably the biggest hurdle and challenge to overcome.
Yeah, I mean, I agree with all the three, what you said so far. If you want to get kind of more into like the nitty gritty of like the actual details, we kind of came up with a conclusion kind of towards the end of our project that we tested this, it was working, it was safe, and we weren't really getting a scarring angle. And we were like, what's going on? Because we knew the particles were getting through, everything was spinning, we had the slots. Turns out, with how thick that we made this slotted disc, particles didn't have enough time to get through before that wall of the slot collided with those particles and actually just destroyed all the momentum it had, and that's why we weren't getting a scarring angle. And so simple rotational kinematics showed us, oh yeah, we only have so much time to get those particles through, and if the particles are only going so fast, they're not getting through. And so a big implementation was actually narrowing down the width of that slotted disc, and boom, our results started to come through, and so that was really cool.
I think one of the best parts about our project was the flexibility regarding the design of. So mostly when you come to college, you're thrown into the theory about how things work and whatnot, but you don't really get to build anything. And so for our senior project, it was really nice to have an open-ended problem and actually go into the design and manipulate that design to function as what we want and and for it to process information that we need to use. And so I think one of the coolest parts about our project was just problem solving each component to see, like, hey, this is not doing what it was intended. What can we make to make it different? And so one of those things that are highlighted is actually our shaft design, in which we needed variable distances between these discs, and a step shaft design was just not feasible to do that. So the team came together and we decided to go with this threaded shaft, which solved our problem. And I could keep going on and on about the entire design considerations, but it's been really fun to just go in with an initial design, see it didn't work, and then just go back to the drawing board and do it again.
Well, thank you so much. I really appreciate your project. It's very, very cool to see that it came together. So thank you so much. We'll conclude our College of Engineering post petition. Thank you for joining us today.